Okay, there we go. Everyone seeing the screen?
Yeah.
Good.
Okay. Well, let me welcome everybody to this seminar, Sonoran Seminar, Mathematical Physics and Geometry. Today we have the both personal and academical pleasure to have Brian Hall with us. I mean, we know Brian since a long time ago, like 25 years ago or so. And then, so Brian has done many interesting things in mathematical physics. One of them, where he's a real an expert, is about the Segal-Bargmann analysis. And today, Brian is going to speak about Segal-Bargmann transform on the unitary group in the large n limit with application to random matrices. Please, Brian, go ahead. And so it's a real pleasure to have you with us. So I ask everybody to mute themselves. And if somebody wants to ask a question, please go ahead. And please also remember to mute yourself after you say your comment or ask your question. Please, Brian, go ahead.
Okay, great. Thank you very much, everyone, for coming out and for inviting me to this. So I'm going to give some references. This is work. Most of what I'm going to talk about is work with Bruce Driver and Todd Kemp that are both at University of California, San Diego. And there's some other papers there that you can find on my webpage. And there is some related work. I really don't have time to talk about it, but there is some related work on this in the physics literature that you can look at there. So I'm also going to make a bit of shameless self-promotion since I'm here about my books. I wrote a book on quantum theory and another book about Lie groups and Lie algebras. So if you're interested, you can take a look at those. Okay, so here's my outline. I'm going to talk about the Segal-Bargmann transform for a compact type Lie group. I'll explain what that is in a second. Then I'm going to talk about the large n limit of that transform. And then I'm going to talk about what this has to do with random matrix theory. I'll try to explain everything, you know, a little taste of what random matrix theory is, for example, in case you don't already know, I will try to explain a little bit. Okay, so I'm going to start with a Lie group, a connected Lie group of compact type. Okay, and there's various equivalent definitions of what compact type means, but the simplest one is it just means it's compact cross Rn. Compact group cross just Rn, commutative group Rn. Okay, and then we have the Lie algebra of this group, and we're going to fix an add invariant inner product, which exists because it's of this form. That kind of group admits an add invariant inner product. And then I'm going to introduce very important thing here, the complexification of K. And I will not attempt to define this in general. I'm going to just define it by example. Okay, the only examples you need to know for this talk are if K is Rn, then Kc is Cn. Okay, that's complexification. You go from Rn to Cn. Okay, and the other example is if K is the unitary group, which is just all n by n unitary matrices, then Kc is GLN, which just means all invertible n by n matrices. Okay, and if you like to think about the Lie algebra level, then it's simple. The Lie algebra of Kc is just K plus Ik. Like when you complexify the Lie algebra, it's pretty easy to complexify the Lie algebra. For the group, it's a little more subtle, and therefore I don't give a general definition. Okay, now when you have a Lie group and you pick an invariant inner product on the Lie algebra, okay, so I said we picked the inner product on the Lie algebra, that determines a left invariant metric on the whole group. And in this case, because the inner product is add invariant, then you actually get a bi-invariant metric. So the inner product determines a metric, and from the metric, you can compute a Laplacian, okay, which we denote by delta. And then I'm going to form the so-called heat operator. E to the t Laplacian here is the heat operator. What it means is that you basically, it's the operator that takes an initial condition for the heat equation and maps it to the solution at time t. So it's sort of the solution operator for the heat equation. Okay, and now I'm going to define, I'll give you an example in a second, okay? If this is too abstract, I'll give you an example in the next slide, which is I'm going to take a function on L2 function on the group. Okay. Doesn't have to be continuous or anything, just any L2 function. And I'm going to run the heat equation. Remember, the heat operator just means you run the heat equation for time t, starting with the initial condition f. Okay, and then you fix the time and you get a function we call e to t Laplacian. Okay, now the heat equation, it's a smoothing equation. So even though this f is just an L2, it could be discontinuous or whatever. When you run the heat equation for even a small positive time, then the solution becomes smooth, and not just smooth, but it becomes real analytic, and not just real analytic, but it actually admits a holomorphic extension from K to KC. Okay, and if you say, oh, I don't believe that statement, how can that be true? Then I'll show you on the next slide how that is, okay? So the transform we're gonna define is the Segal-Bargmann transform. I call it CT, it's a Segal-Bargmann transform. You take a function here on L2 of the compact type group, and then you apply the heat operator, and then you holomorphically extend in the space variable from K to KC. Okay, now let's see what that really means. In the case, K is R. Okay, and K is R, KC is C. What does this really mean? Well, I'm going to solve the heat equation with initial condition F. How do you solve the heat equation with initial condition F? Well, take a class on partial differential equations. They'll tell you how to solve the heat equation on the real line, which is you do this integral, which is a convolution. It's a convolution of the initial data F with this Gaussian function, okay, with an appropriate normalization factor out in front. Okay, that's a totally standard formula for the solution of the heat equation with initial condition F. And what's different is that I want to take now, I want to holomorphically extend after you apply the heat equation. I'm not holomorphically extending F. After you apply the heat equation for time t, then I want to holomorphically extend from R to C. And what does that mean? It really just means I just want to take the Z to be in C, not R. Okay, which I can do because I just put the Z complex in that formula, and it makes perfect sense. The same integral makes perfect sense whether Z is real or complex. And furthermore, you know, this function, it's holomorphic function of Z inside the integral, right? That function for each X is a holomorphic function of Z. I think you will agree. And therefore, as long as the integral converges, it'll still be holomorphic after you integrate out the X, and that's the transform. Okay, so that was an explicit formula for the particular version of the Segal-Bargmann transform that I want to use. And more or less, if you work on any compact type Lie group, it's sort of the same thing. You have a heat kernel, fundamental solution of the heat equation, and you do a convolution, and you sort of holomorphically extend the convolution formula in one of the variables. Okay, now some of you may be used to thinking about this sort of thing in terms of coherent states. So you're integrating the function f against this whole family of functions, right? For each z, you do this integral of f against this function. Okay, and that function, you know, you can include the normalization constant or not. That function we can therefore think of as a coherent state with parameter z. Think of x as the variable, z as the parameter. So it's a real variable, but has a complex parameter. And those are the coherent states, or a family of coherent states. So I will draw a picture for you of that coherent state. I put t equals 1 in the formula, and I put z to be 10 plus 20i. And let's just understand what is the effect of each of those variables. Okay, so you have the 10. The first thing is, oops, sorry, I hit the wrong button there. And I'm not sure what happened, so I need to get my
start.
Yeah, it'll come back up. I had some command key that did, I don't know what it did, but
Sonora, there we go.
All right, so I'll try to be more careful with my keyboard here. Okay, so let's start with the 10 here. Z is 10 plus 20i, the real part of Z. The real part of Z controls where the coherent state is centered. Okay, and then the t, which is 1, is here. And what is that t? The t is the standard deviation, or the width. So the width of this Gaussian, like, is from 10 to 11. That's like distance 1. That's sort of like the standard deviation. The width is controlled by the t. And then finally, the imaginary part here controls how much oscillation there is. So if you increase that imaginary part, you get more oscillation in your wave packet. So it's a standard sort of Gaussian wave packet kind of coherent state. Okay, so now the theorem that I proved in my thesis a long time ago is that you can find for any compact type Lie group, okay? I mean, if the group is R, then this is really just what Segal and Bargmann already did. So the interesting case would be if K is compact, Lie group would be the new part. But anyhow, that you can find a measure on KC so that this map is unitary. Okay, so you transform from L2 of K with Haar measure into this space of holomorphic. I don't know if I explained the notation, but script H means holomorphic and L2 means L2. So this means the space of all L2 holomorphic functions with respect to some measure mu t. And it's some kind of heat kernel measure. So it's defined by or constructed by solving the heat equation on Kc. But if you do this for K is R, Kc is C, then you can just explicitly write down the measure here like that. It's Gaussian measure, Gaussian in the Y direction. Just Lebesgue measure in the X direction times Gaussian in the Y direction. Okay. So the idea basically of my thesis was to say that I want to replace all the Gaussians that you would see in the classical Segal-Bargmann transform with heat kernels. Okay, so if you just set things up in the right way in the Euclidean space, and then you say, well, everywhere there's a Gaussian, that's really a heat kernel, then this is how you arrive at this sort of setup. So if you want to interpret this, what this means in terms of quantum mechanics, then I want to think of that you have in classical mechanics, you have the position space and the phase space, or the configuration space and the phase space. Phase space means you have position and momentum variables. Okay, now ordinarily, and when you do quantum mechanics, for example, in my book, you find that the wave function generally only depends on the position variables and not on the momentum variables. Okay, just classical standard quantum mechanics, the wave function only depends on the position variables. Or maybe there's a momentum wave function that depends only on the momentum variables, but not the position variables. And now the Segal-Bargmann transform is saying we're trying to build a wave function that sort of depends on both the position and momentum variables. So in this case, we're supposed to think of K as being like the position space or configuration space, and Kc is the phase space. So that's at least how I think about the Segal-Bargmann transform. Now, as I've kind of already indicated, if you do this for K is Rn, compact type group is compact cross Rn, so your group can be just Rn itself, then it gives you essentially the classical Segal-Bargmann transform the way Bargmann did it, with some minor differences of normalization. And you can also somehow do this using geometric quantization. I don't have time to go into that, but it is an interesting application or connection to geometric quantization. And it's related to Yang-Mills theory, 1 + 1 dimensional Yang-Mills theory. And it also has been used, the coherent states that go with this transform have been used in quantum gravity. So this guy named Thomas Timon and his collaborators have used this sort of thing quite a bit in loop quantum gravity. Okay, any questions at this point before I go to part 2 of my talk? I know I'm going fast, but I have to cover several parts of this. Okay.
Yeah, so good so far.
So good so far. All right. So now I'm going to go to the large n limit. So that specifically means that I'm going to take K to be UN, unitary group UN, and large n limit means I'm going to take that n right there to go to infinity. So the group is UN, the compact group is UN, its complexification is GLN. Now there's one sort of technical but very important point, which is I'm going to take an inner product on the Lie algebra. You have to pick a metric which determines a Laplacian, and I'm going to take the usual Hilbert-Schmidt inner product on the Lie algebra, okay, but scaled by a factor of n. Okay, that n is very important. Okay, and so if you scale the inner product by a constant, it scales the Laplacian by the reciprocal. Okay, the Laplacian and the metric scale oppositely to one another. And so really, if you say, well, I just want to use the standard Hilbert-Schmidt inner product and then make the Laplacian, then I want to scale it by 1 over n. So effectively, I'm scaling what you might think would be the Laplacian by a factor of 1 over n. Now you may ask, well, why do you want to do that? Why would you scale the Laplacian? Why not just use the ordinary Hilbert-Schmidt inner product? Well, let's take a look. Let's take a look at the simplest non-constant function on the unitary group. Someone tell me the simplest possible non-constant function on the unitary group. You can look at the screen or not, as you wish. Simplest possible non-constant function that you could define on the unitary group. Anyone want to offer a suggestion?
Well, by cheating and looking at the slide, I guess just a function that gives you a fixed matrix entry.
Yes, well, okay, right. So there it is. You can, if you have anything simpler, feel free to suggest it. But the simplest possible function would be, just, it's not a constant, would be f of u is just one entry, uij. Okay, and so let's take that very simple function and let's apply the Laplacian with this particular scaling. And then what you find is the Laplacian of that uij is -1 times uij. And the point is we've scaled things so that that eigenvalue is independent of n. And if you didn't do the scaling, then instead of -1, it would be -n. And when n goes to infinity, that would be bad. Okay, so that's the correct scaling. And just to make life interesting, I'm going to use a slightly different version of the Segal-Bargmann transform. There's slightly different versions that I won't try to explain too much about, but instead of using the Haar measure on the unitary group, I'm going to use a heat kernel measure. And then over here on KC, I'm going to use a somehow slightly different heat kernel measure. But the transform is still the same. It's still e to the t Laplacian, and then you holomorphically extend, but the measures are just different. And it's still a unitary map. I've changed the inner product basically on the Hilbert space on this side. I've changed the inner product on that side, and it's still a unitary map. Okay, and then just to make life still further interesting, I'm going to then extend the transform to matrix valued functions. Okay, because somehow it's not very interesting if you don't make this extension somehow. Okay, and what it means is you just apply the transform entry-wise. Each entry, if you're a matrix valued function, you take each entry, you Segal-Bargmann transform each entry, and then you reassemble that into a matrix, and it will give you this matrix valued Segal-Bargmann transform. Okay, now let's do an example so you can understand. This is not so hard to understand in an example. So what I'm going to do is I'm going to take a matrix valued function, okay, matrix valued function of a unitary matrix. So I'm going to take f of u to be u squared. The u is a matrix, u squared is a matrix, that's a matrix valued function. Okay, and then I'm going to Segal-Bargmann transform it. This is a function on the unitary group. When I Segal-Bargmann transform it, it becomes a holomorphic matrix valued function on GLN, right? When I transform it, it becomes a holomorphic function on GLN, which is matrix valued in this case. Okay, so when I transform it, it's no longer a function of u, it's a function of some other variable in GLN. Okay, so this is what you get. All right, so if you take a look, you'll see that it's a combination of z squared. I started with u squared over here, and I got z squared over here. And then there's also this term, which is z trace u, where this trace with a small tr is the normalized trace. Okay, which is 1 over n times the usual trace. Normalized means it's normalized, so the trace of the identity is 1. Okay.
So this is not like the opposite of the normalization you were using in a previous slide where you multiply the trace by n?
Yeah. Yes, it is. But somehow it's still the right way to do it, because I want the identity to have sort of norm 1. And so I really do. Yes, it is the reverse of the scaling I had a minute ago. Okay, so is this a holomorphic matrix valued function? I mean, is z squared a holomorphic function of z, right? I just multiply the entries, some entries of z together and add them up. That's a holomorphic function. Trace is holomorphic. Okay, so it is certainly a holomorphic matrix valued function. And now what I want to do is to let n go to infinity. Okay, so you guys can help me.
Brian first. So u is z in this formula?
No, sorry. The variable on the domain side is a u and un. But when I transform the function, it becomes a function on GLN. Right?
So you're missing a z on the left-hand side?
Okay, fine. If you want, I'll write z here. You're
Yeah,
a physicist, right? Okay.
Yeah, that's a function of z.
Of z.
Evaluated at z.
Yeah, okay, I understand that.
But it's the transform of the function u squared as a function of z. Yeah, sure. I should have put another z in there.
Yeah, thank you.
And all right, now let's let n go to infinity. Can we let n go to infinity? Where's the n in the formula? Here? What happens if I let n go to infinity in that formula? What do I get?
1.
Z squared.
Yeah, 1 times z squared. Correct, because it goes to cosh of 0, which is 1 times z squared. Correct. All right, now what about this guy? What happens if I let n go to infinity here?
Also 1.
Also 1, because it's sinh x over x. X is going to 0, so it becomes 1. Okay, great. You guys are experts on large n limit already. Okay, so I just take that limit and I get a 1 and a 1. And so here's my new answer, right? In the limit, what I get is this. Okay. Sorry, let me just check this. Yeah, okay. Now, you would say, all right, that's it. Great, I'm done. But there is actually one more step in understanding the large n limit, which is that this function, trace of z, there's a very curious thing, but it's very important to understand. This trace of z somehow goes away in the limit. Why? Because the measure that we're using, there's some measure, heat kernel measure on GLN, okay? We're using some measure on GLN, and it concentrates onto this set where the normalized trace is 1 in the limit. Okay, now obviously, you have no way of knowing that. You'll have to take my word for it, but the measure is somehow concentrating around that value. And so when you see trace of z, you're really supposed to say, well, it's basically 1. What it means is the expectation value is 1 and the variance is small. And so it's concentrating around a value of 1. So really, you should just replace that trace of z by 1 in the limit. So that one becomes 1. And now here's the real limit. Okay, get rid of that trace. And what's notable about this now is I started with just a power of u. And the answer after all of this limiting process is just powers of z. Okay, the traces go away, and I only get just power of u going to some combination of powers of z on the other side. Okay, that's what I get here. Only powers of z. So it's like a kind of a polynomial in z. Okay. All right, now,
Brian, and you are keeping t as a constant, fixed.
Yeah, t is fixed. All of this is for each fixed t, you let n go to infinity. So it's a polynomial in t. Sorry, it's sort of like a polynomial in z, but whose coefficients depend on t in some, non-polynomial way. But as a function of z for each fixed t, right? It's a polynomial. Just multiple of z squared plus multiple of z.
Okay.
Okay, and the theorem is, which is somehow closely related to an earlier result of Philippe Biane, is that this sort of thing always works like that, which is if you start with a polynomial, you start with, instead of u squared, you start with u cubed, u to the 4th, or any polynomial in u like that. Then on the other side, after you let all the coefficients, you take the limit of all the coefficients, and then you also let the traces concentrate the way they want to concentrate, that you just get out kind of a polynomial in z, like linear combination of just powers of z. Okay, and of course, in our example, this QT then would be this polynomial that we just saw. That's a polynomial, and then you're sort of evaluating that polynomial on the matrix Z. Okay. All right. So, and we're going to use this notation that the map that sends this polynomial over here to this polynomial over here, we're going to use this GT. That's Biane's notation, GT. And of course, we have some formulas. It's not just a pure existence result. we have some kind of formula for the GT and this generating function, recursive formulas, and we have a lot of information about how you actually compute this QT. Sorry, GT, which determines the QT. Okay, so that's a very, very, very fast version of the large N limit. And now I'm going to answer the question that you all may be asking, which is, well, why would you want to do this? What is the point of doing this? And you know, who knows what the point is, right? Mathematicians aren't supposed to ask that question really, but in case you think, well, what's the purpose of this? I'm going to try to make an application to random matrix theory. Okay. So if you didn't know that Segal-Bargmann transform was related to random matrix theory, now you will see. All right. So what is random matrix theory? Random matrix theory is, well, you pick a matrix at random, and then you look at some interesting property of that matrix, notably the eigenvalues. And you can look at other things, but by far the main thing people look at is the eigenvalues of that matrix. Okay, the matrix is random, so the collection of eigenvalues will also be random, right? All right, now let's take, for example, a symmetric matrix, real symmetric matrix. Okay, symmetric matrices are nice because they have real eigenvalues. So I'm going to take a random symmetric matrix, and I'm going to make the entries as independent as they can be, you know, independent in the statistical sense, as independent as possible, given that it's symmetric. Okay, so that means on the diagonal and above the diagonal, I choose all the entries to be independent, identically distributed. And then, of course, the entries below the diagonal are just equal to the corresponding entry above to make the matrix symmetric. Okay, and let's furthermore choose each entry to be, say, normal. That assumption is not really essential, but let's say normal with mean 0 and variance 1 over n. There's that scaling by 1 over n again that you have to have for this to make sense. Okay, and Wigner, Eugene Wigner in the 50s, worked out how the eigenvalues behave. That when n is large, what Wigner said is that the eigenvalues will have an approximately semicircular distribution on the interval from -2 to 2. Okay, so semicircle means explicit. It means, you know, the graph is a semicircle, which is this graph, that function. Okay, and
Brian, just a simple question.
Yes.
Where does this interval -2 to 2 comes from?
Yeah, well, I don't know. Like, it's not very obvious. Why -2 to 2?
Yeah. Mm-hmm.
Yeah, it's not supposed to be obvious. I mean, this is a surprising thing.
Mm-hmm.
But so no, it's not obvious why it's -2 to 2.
Okay. Mm-hmm.
Okay, that's the theorem. So here's a simulation, right? In Mathematica, say you can just ask it to do Gaussian orthogonal distribution, and in one, you know, second, you can generate a random matrix like this, and then you can make a, you know, you can plot the eigenvalues. You can make a histogram of eigenvalues, and you'll see that, yeah, you know, you get a nice sort of very close to semicircular shape here, you know, with a little fluctuation around it, right? You see the little jiggles up and down here, but it's pretty much semicircular. And if you pick another matrix at random in the same way, it will also have very close to semicircular distribution. So even though the matrices are random, the sort of bulk distribution of eigenvalues becomes non-random in the limit. If n is 1,000,000, then every time if you choose the matrix and make this histogram, the histogram will look the same every time. Now, if you zoom in with a microscope to where you can actually see the individual eigenvalues, you know, at very close spacing, then it will not be deterministic. But at the bulk level, it kind of becomes deterministic. It's always a semicircle. Okay, so this is the, you know, this is the original theorem in random matrix theory. Okay, Wigner, 1950 something. Now, what I want to do is to say, well, okay, but I want to think about it on the unitary group. Instead of symmetric matrices, I want to have unitary matrices. And if you remember, in our Segal-Bargmann transform, we were using this heat kernel measure on UN, okay, which is some kind of like Gaussian-like measure. Doesn't really make sense to say the measure is Gaussian because the unitary group is not a vector space. So what does a Gaussian mean? But it somehow looks sort of Gaussian-like measure in some sense. And it's a probability measure on the unitary group. And so that means that you can think of it as giving you a way to choose a matrix at random, right? A probability measure means, well, you can pick a point at random from that set using that measure as your probability distribution. So what we're going to do is we're going to pick a matrix at random from the unitary group and look at the random collection. It's a random matrix, so we get a random collection of eigenvalues. But we're going to see the same phenomenon that we saw in Wigner's semicircular law, which is at the bulk level, when n is large at the bulk level, you don't really see the randomness, that each picture sort of looks the same as the one before. And then, of course, we can also do it on the GLN side. It has a heat kernel measure over there on GLN. It's also a probability measure. So you can say, oh, all right, we're picking a matrix from GLN, and we're looking at its eigenvalues. Okay, but let's start with the unitary case. This is much easier to analyze. And Philippe Biane computed this. I mentioned his name earlier. He computed the limiting eigenvalue distribution. So he found a measure on the unit circle because the eigenvalues of a unitary matrix live in the unit circle, that describes the large N eigenvalue distribution. So what it means is that you pick a matrix at random from UN using this measure rho t as your probability distribution, and then you look at the fraction of eigenvalues in a given set in the limit as n goes to infinity. And the claim is that fraction somehow becomes deterministic. You say, well, isn't that a random quantity? Well, yes, it is for finite n, but it becomes somehow deterministic in the limit. So this measure is actually sort of deterministic measure. It's like the semicircle. It's some kind of analog of the semicircular distribution that we saw in the Wigner's law. And what Biane showed, I'll show you in the picture, is that in the next slide, if t is less than 4, then this measure does not fill up the whole unit circle. But if t is greater than 4, then it does. So anyhow, that's one of the cute facts about this measure. Something interesting happens at t equals 4. So let me just show you a picture. It's a simulation, okay, of the eigenvalues of a unitary matrix. Here's one for t equals 2. We're using the heat kernel measure with t equals 2. Here we're using heat kernel measure with t equals 4. Okay, and here you see, look, they don't fill up the whole unit circle, right? There's this gap over here where there are no eigenvalues. Okay, and here at t equals 4, it does fill up the whole unit circle. But if you look closely, you can see, well, the density is kind of going to 0 right at -1. So it's just at t equals 4, it just wraps all the way around the unit circle and just touches at -1. And again, it's supposed to be at this bulk level deterministic in the sense that if I did another simulation and did another plot, that at the bulk level, meaning what your eye can actually see, it would look the same as this picture. And this is just a sort of graphical representation of that measure gamma t. There's some probability measure that describes the density of points as you go around, which Biane computed. And there's not really an explicit formula, but there's lots of ways of sort of calculating with it. Okay, are you with me? Questions at this point?
Really silly question that I have. Is this magical t equals 4 value in any way related to the -2 to 2 interval that we had for the symmetric matrices?
I don't know exactly. I'm not sure. Yeah, I don't have a simple way of saying how they're connected. It's an appealing suggestion, but I don't have a definite point of connection there. But it's a reasonable question. Why t equals 4? Like I can show you in some formula, but like, yeah, it's not obvious. All right, now this slide, if you want, you can just sort of tune out a little bit for this slide. But I want to tell you how Biane computed this measure. Okay, so there's something called the Herglotz transform. If you have a probability measure on the unit circle, you can compute this integral. Okay, so you take z plus zeta over z minus zeta d gamma zeta. Okay, which will be a holomorphic function of z. Right, you integrate out the zeta, it's a function of z, and it will be holomorphic. There should be a t there that I failed to write on this side. Sub t, right, depends on t. And it's a holomorphic function of z as long as z stays outside the support of the measure, right? So as long as the z and the zeta do not be equal, then it's a holomorphic function. Okay, and there's an inversion formula that says if you can somehow compute the Herglotz transform of this measure, then you can compute the measure using some inversion formula. Okay, it's probably in Rudin's Real and Complex Analysis book. You can find such a thing. Now, Biane computed this Herglotz transform. Again, depends on t. Okay, he computed it like this. It's chi t of z plus 1 over chi t z minus 1, where chi t is the inverse function of some explicit holomorphic function here. Okay, now again, this is sort of maybe too technical a slide to put on such a talk, okay? But the point is that when you try to compute this measure gamma t, you naturally encounter this function ft and its inverse, okay? Here it's just an explicit holomorphic function, and then you try to invert that function. Okay, so in some technical computation, you get ft and its inverse function, which we call chi t. Okay, now the Herglotz transform is holomorphic except on the support of the measure, so this chi t better also be holomorphic outside the support of the measure. Right, so this chi t, which is the inverse function of some explicit function, it's going to map you from the complement of the support. Okay, you take the whole complex plane, you take out the support of that measure. So I'm drawing a picture like for t less than 4. And it's going to map that complement of that support to the complement of some set. Okay, which I call sigma t. Okay, so what is sigma t? You take the sort of the image of chi t on c minus the support of gamma, and then you take the complement again. Okay, so chi t takes the complement of the support of gamma t to the complement of sigma t. Okay, so you say, all right, I don't know, what's the point of this? You'll see why this is relevant. But let me just draw you some pictures and see that, well, okay, this domain, it's simply connected for t less than or equal to 4, and it's doubly connected for t greater than 4. So it all, because it's connected to the support of the measure gamma t, then it has a similar sort of transition at t equals 4, that it just, the domain sort of pinches off at t equals 4. Okay, now you may say, all right, look, this is a kind of technical thing. This domain sigma t comes up in some kind of technical calculation about the measure gamma t. And the question I'd like to ask is, well, is there some deeper significance to this sigma t? Like, what does it mean? The gamma t, I know what it means. Like that support of gamma t, that's where the eigenvalues of a matrix from the unitary group live, right? When I pick a matrix at random from the unitary group, its eigenvalues live in the support of that measure gamma t. What about this set sigma t? Is there something meaning to that? And the claim I'm going to try to justify in the rest of the talk is that sigma t is where the eigenvalues of a random matrix from GLN with its heat kernel measure will live. Okay, that's the point of this part 2. That's the application of random matrix theory that I'm heading for, is if you pick a random matrix from GLN using that heat kernel measure, where will the eigenvalues live? And this, we're going to try to answer that question. So here's the simulation. I've done 2 values of t close to 4 because t equals 4 is kind of the most fun value to use. And here's the domain, and here are the eigenvalues. And you say, oh yeah, the eigenvalues live mostly in the domain. There may be 1 or 2 that are just outside the domain. Maybe right there's one that's a tiny bit outside the domain. But as n gets larger and larger, they're more and more clustering into that domain. Okay, of course, it's just a simulation now. We want to try to prove something, but that's what this picture is supposed to be telling us. Okay, that's what I want to try to prove. So let me see if I can explain how the Segal-Bargmann transform can help us understand this assertion.
Let me ask you something, Brian. From the picture that you had in the last slide, you see some concentration of points in some region where you have this, right? I mean,
yes. So there's a much higher density of points, of course.
Exactly.
It's nowhere nearly uniform on this region. That's true.
And do you know the meaning of that?
Well, I'll tell you at the end, if I have time, that how you figure out the distribution of points.
Great, thank you.
But the Segal-Bargmann transform isn't going to tell us that. That has to be some other calculation. Okay, so now remember this large N limit Segal-Bargmann transform, which originally took polynomials to polynomials. Biane showed that it extends to a map of L2 of the unit circle into holomorphic functions on that same domain sigma t that I was just telling you about. So what does that really mean? What are we really talking about here? What I mean is that you take, instead of like f of u is u squared, you take some other kind of like functional calculus function. Functional calculus means you take a function of like a scalar variable and then you plug in a matrix into that function. So here's the example I'm really most interested in, which is you take 1 over u minus lambda, and then you plug in u as a matrix. So I get u minus lambda inverse. Okay, that's like a functional calculus function. It's a function of one variable, but then you sub in a matrix for that variable. But it's not a polynomial. Okay, that's the point. Is I want to go beyond just powers of u and get this other functional calculus function. Okay, and if you do that, the point of this measure here, this gamma t, is that if you take one of these functional calculus functions like that one, and you take this L2 norm in the L2 norm over un, and you take the large N limit, it becomes the L2 norm just of that one variable function over the unit circle. Okay, and that's somehow trivial, more or less trivial thing. I mean, computing the measure gamma t is not trivial, but this statement is somehow easy. Okay, now what Biane shows is that, if you take any function like that, it transforms to a holomorphic function on sigma t, f, and you sort of think of that holomorphic function as representing a functional calculus function on GLN. And you do not get the same kind of limiting property of the norm here, but you can ignore that last statement because I'm just not going to use it. But the large N limit of the norm doesn't work the same way because the matrices are not normal and you don't have an orthonormal basis of eigenvectors. Then when you change basis, the Hilbert-Schmidt norm isn't preserved or something, okay? But the main thing I want to keep in mind is this positive result, which is that in a limit, you can compute the norm on the UN side that way. Okay. All right, now the theorem we're trying to prove is that as n goes to infinity, when you pick a matrix at random from GLN using this heat kernel measure, that is n goes to infinity, the eigenvalues are going to cluster into this domain sigma t. Okay. And how to prove that? We're going to try to prove that using the Segal-Bargmann transform, this large N Segal-Bargmann transform GT thing. Now, let me remind you that we saw this function ft. We had this explicit holomorphic function ft, and chi t is the inverse function. And by definition, chi t takes the complement of the support of that measure on the unit circle to the complement of sigma t. So really what we're saying is, the complement, so chi t takes the set where the eigenvalues from un don't live, right, outside the support of that measure to the set where the eigenvalues don't live on the other side, which is the complement of sigma t. Okay, now, the key formula to prove this is this one, which is proved in Biane's paper, and we reproved it in a different way in our paper. This is Driver, Hall, Kemp paper, is that if you take the inverse Segal-Bargmann transform of this function 1 over z minus lambda, okay, you get this function RT of u, which is given here. Okay. And notice there's a very close similarity. This function is 1 over z minus lambda. Okay, this function's almost the same kind of thing. There's a constant here in front. It doesn't really matter. And then it's 1 over u minus ft of lambda. So that 1 over blah minus lambda kind of thing transforms to something similar on the other side. And the point is, this is well defined. If lambda is outside the domain sigma t, then ft of lambda will be outside the support of the measure. And so this is a well-defined L2 function on the unit circle with respect to gamma t, because the u and the ft of lambda will not be equal. Okay, so now here's the point of that. Okay, here's the proof of the theorem. Of course, I'm lying a little bit, but not too much. Okay, so you take the, remember, when you have this holomorphic function, what does it really mean? It's you're supposed to take that holomorphic function and make like a functional calculus function, meaning you're supposed to plug a matrix in to that function. So when you see z minus lambda inverse, I'm supposed to put in a matrix there. Okay, and then I want to compute the norm of that matrix valued function. So I compute Hilbert-Schmidt norm and integrate that, the L2 norm of this z minus lambda, and then I let n go to infinity. Okay, and then I use the fact that the transform is isometric, so I can change the transform over to something on the other side, and I'm going to get this. Okay, and we just said that that thing, whatever it is, I don't know if you can calculate it or not, but whatever it is, it's finite, because it's just the L2 norm of this function. It's just the L2 norm of this function. And the ft of lambda is outside where the u lives, and therefore it's a bounded function, and so it certainly has finite L2 norm. Okay? So that means that sort of in the large n limit, the L2, this integral has to be finite, right? But of course, if lambda is in the spectrum, if lambda is an eigenvalue of z, then this inverse doesn't make sense, and therefore the Hilbert-Schmidt norm is infinity. So the fact that this integral becomes finite, it has a finite limit as n goes to infinity, means that when n is infinity, that lambda is not an eigenvalue. Okay, so that's the proof of the theorem. If you have this lambda, which is outside the closure of sigma t, then this thing must be finite so that this integral can be finite in the limit. And therefore, it must be that when n is large, that that lambda is not going to be an eigenvalue. Okay, you with me? Questions? All right, again, I don't know how, maybe this is too much technical information, but it's just trying to show that, all right, look, how do you prove the main theorem that the eigenvalues cluster into the sigma t? Well, you use this large n Segal-Bargmann transform, and it somehow tells you that.
Brian?
Yeah.
How are you cheating here?
I'll tell you at the end.
Okay, thank you.
Yes, I would be happy, but let me tell you at the end.
Okay.
I'm glad it's not so obvious that I'm cheating. That's comforting. So I'm now going to spend a couple minutes to tell you some further results that we've gone in this direction, which is what Carlos asked, which is, well, okay, the eigenvalues live in that domain sigma t, but how are they distributed in that domain? They're clearly not uniformly distributed over sigma t. How are they distributed? And the answer is they have a very special form. Okay, this is a totally separate paper that does not use Segal-Bargmann transform at all. It's a different paper with Driver and Kemp, using a totally different method that says that the limiting distribution has this special form. So here's the Lebesgue measure on the plane, r dr d theta in polar coordinates, and it has this density, 1 over r squared, times some function of theta, which I'll tell you about in a second. Okay, and if you like, you can write that, you cancel the r and the r squared to give a 1 over r, and then it becomes d log r. If that floats your boat, you can write it that way. for some function wt. So it's already kind of surprising thing that, that it has this very special form in polar coordinates. And what is wt? Okay, you're not going to really be able to digest this formula, I know that, but the claim is that it's totally determined by the geometry of the domain. Okay, so here's the domain, and you compute this function RT of theta. It's the outer radius of the domain. You take an arc with angle theta, and you look at that outer radius there, that's R sub t of theta, and then there's some formula here for the density in terms of that RT of theta. So the point of this is, in theory, if you understand the domain, then you understand RT of theta. In theory, you can compute this WT. Like on your computer, you can compute this WT easily enough. Okay, so here's a plot of that formula. Okay, so here's t equals 1, and you see this kind of big spike here. That's what Carlos was asking. There's a much higher concentration around that point. And in the formula, where does that come from? That spike really mostly comes from this factor of 1 over r squared in the front of the formula. Right, near the origin, that 1 over r squared is much bigger. So that really, you always see a big concentration near the origin, but it's really all mostly because of that 1 over r squared. Okay, here's t equals 4. That's the most interesting case in some respects. And there you see, like, wow, it has a lot of variation around that little hole, right? The density is very small over here and very big over here. And that's what you get. And a consequence of the formula, right? When I wrote it the second way, it was d log r d theta. It was just wt of theta d log r d theta. And from that formula, you can see that if you take the log of the density, the log of the eigenvalues, this complex log with your favorite branch cut, you take the complex logarithm of the eigenvalues, then the density will be constant in the horizontal direction. So if I travel horizontally here across any line, the density of points horizontally should be constant. The density is not constant everywhere, right? It's much smaller up here at the top and the bottom than it is in the middle. But across any given horizontal line, the density of points should be constant. This is the consequence of that formula that I just wrote down. And one more slide, and then I'll stop, which is, this is a paper of Ho and Zhong, Qingwei Ho and Ping Zhong, did a similar problem in which you pick this matrix at random from GLN, and then you multiply by some other unitary matrix. And it gives you lots of more interesting pictures. So here's a picture where the unitary matrix has eigenvalues at like plus or minus 1, plus or minus I, and you get all kinds of cool pictures. So there's been a lot of activity in this area in the last few years, and a lot of sort of extensions of this, but it all started somehow with Segal-Bargmann transform. So I think I should stop there, and thank you very much for listening.
Thank you, Brian. Okay. So questions, comments are welcome.
Maybe I should now answer Steve's question.
Please, that's the first question, maybe, Brian. Please go ahead.
Okay, first question. Let me go back to that slide. Yes, here.
Yeah.
Okay, so I'm lying here because actually this quantity here, this integral, is actually infinity for every n and lambda. Because even if lambda is outside the domain, for any finite n, there's always some positive probability that there could be an eigenvalue really close to lambda. You see what I mean? Like, it may be very low probability, but like anything can be an eigenvalue. For any finite n, any non-zero number can be an eigenvalue. And so like this is not actually a well-defined holomorphic function on GLN, right? Z minus lambda inverse. That is not a well-defined holomorphic function because there are matrices in GLN for which lambda is an eigenvalue. And so actually, like, it doesn't have a L2 norm, or if it does, it's infinity. So what it really means is you somehow have to let n go to infinity first. And you get some limiting object that the z, you take the z and you let n go to infinity, and you get some sort of limiting object that lives in some operator algebra. And then you do the same calculation in that operator algebra. So Z, instead of being a random matrix, is some operator in some operator algebra. And then the Z minus lambda actually exists, and this same formula holds. So that's where I'm cheating.
Okay. Thank you, Brian. Now questions, please.
Yes. So this answer actually gets at my question.
Please go ahead, Matthew.
I'm sorry?
Yes, go ahead.
Yeah, go ahead, Matt.
Yes. So this gets at my question, which is that I've always wondered when I've seen talks on random matrix theory, it seems like, so I'm interested in direct limit groups. It seems like there ought to be a way of formulating this in terms of direct limit groups as telling you something about, say, objects that live on the group U infinity, for instance. But I've never seen these sort of large n limits in random matrix theory presented that way. And I'm wondering if there's any way of doing this.
The answer is, I do not think so. There is some kind of limiting theory in which you have an actual operator. You know, there is some like limiting object. The theory has some kind of limiting object in which there's a Z that sort of you can pick that sort of represents, well, n is now has the value infinity. But that limiting object, it's not like a random matrix from U infinity. And one way to understand why that's not so is that, like, we always use, for example, the normalized trace. And if you're in U infinity, like the identity doesn't have a well-defined, you can't really take the normalized trace if n is infinity. I mean, I don't know if that's a helpful way of saying it, but like, yes, there is a limiting object, but I just don't know any way to make it live on the group U infinity.
So, I mean, there are other ways of embedding the UNs into each other, right? You can embed them sort of diagonally, and when you normalize the trace that way, well, then in the limit, you get this group called U of 2 to the infinity, where the identity has trace 1. This is sort of how you construct, this is sort of related to how you construct the hyperfinite 2-1 factors, right? So I don't know if that might help. But the other thing that comes to mind is that it is possible. So one of the problems with this group U infinity or U2 infinity, et cetera, is there's no Haar measure, but there's still, it turns out there's a construction of a U infinity invariant measure on a sort of completion, a sort of projective limit completion of these things, which is U infinity invariant. And so I don't know, maybe there's some way of making this work. And maybe there's a way of writing these measures on that completion of U infinity.
Okay, but here's another interesting thing. The way people generally do these things in these operator algebras, the limiting object is an operator in operator algebra. And the thing is that, you know, Z is a random matrix, but the limiting object is not a random operator from the operator algebra. It's just one fixed operator from the operator algebra. And that one fixed operator reflects the fact that the bulk eigenvalue distribution becomes deterministic in the limit. So in a sense, I don't want it to be a random element of U infinity in the limit. I want it to be something deterministic because that reflects the deterministic nature of these large n behaviors. But I'm not saying it can't be done. I'm just saying it is. I don't know enough about these sorts of things that you mentioned to know that it couldn't be done in a way that sort of keeps it closer to the actual U infinity, but it certainly not. Usually there's some, you know, the unitary group is so far removed. It's some very abstract operator algebra. You don't really know what it is.
Okay, thank you.
More questions or comments, please?
Yes, Brian,
Yes.
what can you say about the case t equals 0?
Well, I mean, t equals 0, it's a delta measure and a delta measure, right?
Yeah.
So probably everything that
And this G sub t is the identity, right?
Yeah, and
Just-
so like the identity map takes the complement of a point to the complement of a point. You have a delta measure at 1, and the map f of z, f t of z equals z, will map the complement of a point to the complement of that same point.
Yes, right.
So
And
it's still be true.
this map acting on polynomials is also the identity, is that right? You said the map extends to polynomial when you were in part 2.
I mean, there's something somehow pathological about the polynomial aspect of it, because, but yes, the map formally is the identity because you're applying e to the t Laplacian with t equals 0, and it's just the identity.
Equals 0. Right, right.
Mhm.
I asked because t equals 0 is like the classical limit of what you're doing.
Yeah, I don't know.
According to you, t is, well, you didn't say this in this talk, but people should understand that in other papers, or maybe it's even in your original paper, you can interpret t as Planck's constant.
Yeah, I don't know. I don't know if there's any interesting, I don't know of any interesting way of letting, getting anything interesting out of t equals 0. I don't know. That's a good question.
Okay,
Yeah.
thank you.
More questions, comments, please? Well, Brian, I mean, your interesting results. I would like to see them in action, like in some particular cases or applications. Like, I don't know, I'm curious to see if one can see it in the chaotic systems, like you mentioned in your papers as well, and then to see the interpretation of your results over there. Have you considered that possibility?
Not exactly. I know that random interest theory has some connection to quantum chaos, but I don't know how that would fit into this.
Mm-hmm.
A lot of the quantum chaos stuff, it has to do with the microscopic behavior of the eigenvalues, which is you zoom in with a magnifying glass until you can actually see the individual eigenvalues, and then they're still random at that scale.
Mm-hmm.
And this theory is more about the bulk behavior.
Mm-hmm. Yeah. Mm-hmm.
I don't know, maybe there's some way to bring that into the story as well.
I see. Yeah. And also related to Steve's comment about thinking of t as the Planck's constant. Well, it seems that I don't see some, semi-classical thing here, but it from what I see from your results, the variable t, you have some phase transition there before and after t equals to 4, right?
Yeah.
So that's very interesting. Uh-huh.
Yeah, I don't know what it means. Physicists call it topological phase transition, but so that's certainly one of the intriguing things. But and that it's the same t equals 4 on the unitary side as it is on the GLN side. I mean, this Segal-Bargmann transform sort of makes it clear the unitary and the GLN are so closely connected that you can immediately see that when the t equals 4 transition happens on the unitary side, that you're going to have a similar transition on the GLN side.
Mm-hmm. Yeah, okay. Well, thank you, Brian. Well, more questions or comments?
Just one quick question.
Okay, go ahead, Matt. Mm-hmm.
Very interested in about the details of this operator algebra that you say you're using to somehow formalize this large n limit, and that things become deterministic somehow. Would you have any good reference to read about the details of how this sort of works with the details?
Well, it's probably in some of Biane's paper. I could try to send you something. I mean, Biane works sort of in a Hermitian case, sort of more like Wigner thing, and takes a large n limit. And then you somehow solve a stochastic differential equation to get the unitary Brownian motion, and then you set it equal to t equals 1, or then you evaluate at a particular t. So you build some, it's in some very big operator algebra, and then you make a Brownian motion, and you solve an SDE, and then you evaluate it at time t. So it's very far removed from the unitary group in the sense that you build this thing that's like Hermitian matrices, and then you solve an SDE to go from Hermitian to unitary. So you aren't building, you could try though to build the unitary matrices in from the beginning, but but I could try to send you, you can look in some of the papers of Biane, and you're solving an SDE, and the driving Brownian motion of that SDE is in some operator algebra that's built with a Fox-based construction.
Okay, thanks.
But
I'll take a look at those papers.
Maybe look at like the the paper Biane, in which he introduces the free unitary Brownian motion, which is in the Fields Institute paper from the 90s. I can send you a reference if you have any trouble finding it. So you build one big operator algebra, and then inside that you solve a differential equation, and you get this unitary thing.
Okay, thank you very much.
Carlos, are you mute? You're mute. You're mute.
Well, thank you everyone for coming out. I appreciate the questions and the comments.
Thank you, Brian. I would just like to step in for a second. Some things are a little more difficult to do online than in person. But my colleague at CMOT, Matthew Dawson, is interested very much in these questions. And he's here today because I made sure that he would be here today.
Well, thank you very much. I appreciate it.
Carlos said, I believe you and Matthew have not met before either. No, so Matthew works over in Merida, in a branch of CMOT, which is quite far away from Guanajuato, quite far away at the other edge of the country. But he was actually with us in Guanajuato for a few years as well, where he was working with Raul Quiroga, and he continues to work with Raul in Topless operators in the relationships to Lie algebras. Okay, so
Thank you for the introduction. Very nice to meet everyone, and
okay,
thank you for the nice talk.
Why don't you read what's in the chat? There's a question, and there's an answer to the question about some things in the book of Mingo and Speicher about freeness that might be relevant to your question.
Wonderful, thank you.
yeah, thank